Okay. Okay, hello everyone. Last day, last official day in this course. So I start with asking whether anyone had some experiences with the scripts or with a running translog or input log, uploading data, aligning data with a TPRDB. Can you hear me?
Absolutely, yes.
Okay, excellent, good. Thank you. No? Okay. So if nobody has any questions with respect to what we discussed the past couple of days, weeks, 2 weeks? No? Okay.
Could I ask a question? I'm not sure. I may have missed the answer, so yeah, I was just wondering if you have participants that, for example, I have some that are translation students and some that are professional translators. Is there a way of either when you upload to YAWAT or when you're actually dealing with the tables, is there a way of encoding the two different groups somewhere in the data?
Well, so you have two groups and they produce translations and you want to disentangle those. Yeah, so what we did, I mean, they all have different file names, and then you know which one is participant 1 and participant 2 and so on. And somehow you could then know that participant 1 is in one group and participant 2 is in the other group. That is not directly coded in the data, but that's something you would know, I guess. And you could annotate this and disentangle these two groups. We have also lots of metadata for the translations that we have. In the TPRDB, there's a folder called metadata, and that contains, for quite a few of those studies, it contains metadata. So the way we asked for this. So how many years of experience do translators have? What is their educational background? In the beginning, we also had the question with eye tracking whether they wear glasses, so as to know what the expected translation or eye tracking quality is, and so on. So what is their first and their second language, how many languages, and maybe their third language, and so on. So there's a couple of categories. They would fill this in questionnaires. And this is available also in the TPRDB in a folder called metadata. And you could use this kinds of classification or have your own. And once you have this, then you would just merge this into the tables. Ah, Fabio is there too.
Yeah.
New haircut.
Yeah, new haircut.
Wow, in Hong Kong.
Yeah.
Okay. Already quite late in Hong Kong in China. Does this answer your question?
Yes, it does. Thank you very much.
Okay. So otherwise, today we want to talk about the free energy principle. And for those who want to get a certificate for this course, it is linked to the homework. I should record this maybe. I record here. So, okay. So again, today we talk about the free energy principle. And for people who are who want to have a certificate in this course, they it's part of from here we develop homework that is to be produced until the end of July. I don't know how many people there are who want to have this kind of certificate from Saarland University or maybe from India too. So the idea today would be to talk about this free energy principle. And I will give an introduction to the ideas, to the basic ideas. And then Yusheng was friendly enough to lead us through a package called, what's it called? PYMDP, Python Markov Decision Process, which is, as here we have on this slide here, a package that implements a partial observable Markov decision processes. So the idea today is then, so what we have looked into so far in this past sessions is we looked into the translation data from a process, from a product point of view. So we looked into segments and also into ST tables. But we can also look into this process data from the process angle and look into what are the perception action loops in the translation process data that we can see. And so the idea then in this partial observable or in this free energy principle that is the question, how do translators go about these perception action loops? And the idea would be that they should minimize the surprise. And then we want to talk about partial observable Markov decision processes and possible homework. So we looked into these tables or into the process in this way. In these progression graphs here, we have a progression graph that were a quite fluent translation. So in the beginning, a translator reads a little bit in the source text, but then...
Sorry to
Yes?
interrupt. Are you sharing your screen? Because I can't see it. Others chat also can't.
Yeah, okay, it's not shared. I'm very sorry. So you should have said it from the beginning. Doesn't make sense if I point at the slides and you don't see it. Okay. Yes, thank you. Okay, so here we have a progression graph, and we can see that the translator here reads a little bit ahead in the source text and then very fluently types in a translation here again, reads the source text, types fluently the translation with no much of hesitation or revision. There's also no revision phase. So if we look into this a segment here, then into this segment here, then we can see that we amplify this segment here and we can see this part here. I just closed the window. There's too much noise from outside. So we see here that the translator reads a piece of the source text, gets ready, gets some idea what the source text is about. And remember, the blue dots are fixations on the source text. And then types in quite fluent here a piece of text by looking at this at the target side here. There's in red are deletions. You can see how something is typed in and then deleted again, and this triggers then fixations on the target text, I suppose. And then again, the translator looks at the target text and at the source text, sorry, and reads ahead and types in the translation. Here again, then there seems to be some surprise, many refixations on this one word, then a deletion. And once this hurdle is addressed, then the translator goes on. So we can see kind of kinds of orientation where the translator takes in new information, fluent typing, and then maybe some surprise, some hesitation, and once this is solved, it goes on with the translation. So we have already seen that we can chop up this translation process in various ways. Here we have what we call translation units, which are characterized by a typing pause in white here, which is more than 1 second, and then a coherent stretch of typing, a typing burst, where each keystroke is less than 1 second. So there is less than 1 second between successive keystrokes. Here we see then we have these typing and pausing, and here we have a line of gaze data. So the translator reads the source text, then stays with the eyes on the source while starting typing, then eventually goes to the target site here, to the source, and so on. So the two streams of data, typing and gaze data, which are apparently two independent streams of data, but of course they're coordinated somehow. So we can chop this up into these translation units, or we can go even further and chop this up into what we call activity units. And here we have six types of activity units. Reading only, so this would be the activity unit of type 1, so where there is only eyes on the source text. Then we have here concurrent reading and typing, so the person reads on the source text in blue dots while typing, then keeps on typing here, but the eyes switch to the target site, which makes then AU of type 6, where we have concurrent reading and typing, but the eyes this time on the target side. And then the translator, as you can see here, goes back and forth between source and target text while keeping on typing. And then we have here again the eyes on the source text, activity units of type 1. And then, so we have these sequences of activity units. And as you can see here, they chop up translation units into smaller segments. Now, okay, so we can use these kinds of activity units or translation units to characterize the translation process, how the translation evolves in time, right? And these kinds of activity units and the characteristics of these units will characterize how difficult this translation is for the translator to produce. So it's some kind of a translation effort. It reflects some kind of effort that is there. So how does this look from the point of view of the free energy principle? We have this, here is the idea that a translator goes on in, say, an agent, not only a translator, but any kind of agent, has a kind of observations, action. So there is a cycle of perception, action, and this cycle, then with this cycle, then the agent controls their environment and can survive in that environment. So if the agents, the action should be somehow consistent with the observations, and so we have this cycle here. In the translation process, it would be, well, we can maybe see this very similar. So instead, the agent would be the translator, and the environment would be the source text, and then the actions would produce a target text, the source text, and then the environment. So in which environment is this translation being produced? What are the context maybe could be, are there translation tools to be used, and so on. So we have this same loop of observation and actions here for a translator. But now there's not only observation and action, but according to the free energy principle, there is also a prediction and an observation. And so there may be a clash, a discrepancy between the prediction and the observation. So a translator may come into a translation situation and think of the text in a certain way. Maybe it is will be easy and so on, or maybe it will be of this and this type. But then what they see is actually something different. So there may be a clash between the prediction, what the translator predicts, and what they observe. But in the ideal case, the prediction would lead to an action. So the translator predicts maybe the next chunk, how it should be translated. The action would be changing the world. So inserting a piece of target text, a piece of translation. Then the translator will observe their translation together with a new target text, and then go on in this kind of loops, in this kind of loops. If everything works nicely, the observations will be similar to the predictions. So there's so also the translator will change the text, and he or she will observe their translation. And if there's a clash, then also either perception can change the beliefs. So if there is a clash between the predictions and the observations, the translator can change their beliefs. Means maybe their imagination, what the text is about, how dense the terminology is, or what it is about. So either the translator can change their beliefs to reduce, to make smaller this discrepancy, or they can change the world. So they can have an impact on the world so that the world becomes similar to what was predicted. So there's a prediction here, a change of the word, and the observation will then be hopefully inconsistent with what was previously predicted. And so the translator will actually implement a kind of self-fulfilling, or not only the translator, any agency. That's the idea of this free energy principle. The agent will change the world such that it comes closer to what was predicted. Okay, so how does and this is exactly so, this elimination of the discrepancies, this making smaller the discrepancy, is exactly the minimization of the free energy. So it's basically minimization of free energy is to reduce the discrepancy between the prediction and the observation, and this can be either achieved by changing the world or by changing the model, the beliefs of the agent. So how does this look like? So we in the translation process, we have several layers of these action prediction loops. So one loop can be a translation unit, as we have a pause. The translator maybe gets some input and then types out the translation, gets some input, types out the translation. So we have a kind of a perception action loop here on the very small level here, on each level of on a level of a translation unit, or maybe even on the level of this activity units. But then we also have this higher level translation processes, where a translator first observes or orients themselves and gets a gist of the text, of the source text, and then goes into a state of smooth typing or fluent typing, and then maybe there will be something surprise pops up. So the prediction and the observation do not coincide anymore. So there's a kind of an hesitation. And once this hesitation is resolved, maybe through another phase of orientation, then the translator goes on. So the idea is that a translator would like to come into a phase of fluent translation, because this is the phase where translations are produced, and use the orientation phase, the preceding orientation, to have a better idea what to produce. And this hesitation and these kinds of phases are somehow induced by surprise, by unanticipated surprise. So we have these three phases, and in the free energy principle, as we saw before, this orientation activates internal resources, and it serves to adjust a model that the translator has about the text to be translated with the observations. And this can be expressed in terms of complexity reduction. So there is some kind of an expectation, this cue of you, and kind of an observation P of U, and this Kullback-Leiber divergence here says if the expectations coincide with the observations, so if these two distributions, P, Q of U and P of U are identical, then this Kullback-Leiber divergence will be 0, and it means the complexity is small. The complexity here relates to the differences of the expectations and the observations. Okay, so and here the assumption is that this complexity will be reduced through an orientation phase, an epistemic affordance. A translator tries to have some information about the text, so we have some kind of reading of the text, information gain. And this reading of the text reduces the expected risk. So the risk to come into some surprising circumstance, or to have some kind of unanticipated translations and so on. So we have orientation and complexity reduction. On the other hand, we have a fluent production, which can be expressed here in terms of a free energy principle as accuracy. It means that so this 8 that we had before, a translator has some predictions, produces some output, which would be the A. This A is the action here, and the var theta here would be the source text, and then observes the joint product, so the joint prefix of the translation plus the source text, given a certain state in which the translator is. And if there is no surprise, then this accuracy will be maximum. Okay, so if this probability is very high, if the observation corresponds to the internal states, to the expectations here, then the surprise will be low and the accuracy will be very high. And I think we can see this in these kinds of very smooth progression, where the prediction, where we have some kinds of predictions, the translator predicts somehow a prefix the next translation, then observes it again, and there's a smooth typing. This kind of prediction and production of the translation does not produce a surprise or a doubt, something like this. Here we have a different situation where obviously we saw this previously. After some time of fluent translation production, the translator may observe something that is surprising for him or her. So we can see some kind of surprise, some kind of unanticipated situation, and where the observation does not correspond to the expectation. So we can see this in the data as some kind of hesitation. Okay, so if you go back to this cycle here, these two components, complexity reduction and increase of accuracy, make exactly the free energy. So a translator or an agent for that matter wants to reduce the free energy by reducing the complexity, means to make the model similar to the observation. So what is observed should be similar to the prediction. So this clash should be minimized. And on the other hand, the accuracy would indicate that the actions actually fulfill forthcoming predictions, so that we have this kind of smooth loop in which the agent interacts with the environment by only minimally changing maybe the complexity and having some impact on the translation. Okay, so I think this is the idea of basically the idea of this free energy principle. We have two components that impact this free energy: the complexity, which is how well the model coincides with the observations in the world, and how well the actions coincides with the predictions that a translator has. Okay, so now if we look into these lower level of the translation process. So we can look into this higher level here where we have orientation, smooth typing and hesitation. But if we look now into this lower level, we can also see a translation. The translation process unfolds in terms of alignment groups and activity units. And so activity units, I just talked about these. We have these different activity units here where we have concurrent reading and writing. So reading the source text and writing out the piece of translation, and the eyes switch back and between the source and the target text and so on. And here we have a piece of reading source text only. Then we have on this level here, we can chop up this whole process in terms of alignment groups. So an alignment group would be a source target correspondence. And you can see here that the source text was breakdown of traditional norms. Okay, so this was the sequence of the source text. And what the translator types here into Spanish, there is a swap of the noun and the adjective here. So first, rotura de las normas. You see that rotura de las, so this is typed in the order, in the temporal order, las, and then normas. Here is some kind of deletion and insertion deletion that takes place. But this one here is the translation of norms. Okay, so we see in Spanish one needs an article here, las normas. Rotura de las normas tradicionales, which comes here. So the translator types in the translation not in the order of the source text, but in the order of the target text, and reverses. So tries to go over the source text to find the information that allows him to write the next word in the target text. Okay, so we have here kind of syntactic inversion, which I think we talked about last time also when Thomas asked this question with respect to the Chinese, and we had this in the spoken data too. We can see here kind of a syntactic inversion, and where the translator prefers to write in this order of the target syntax, and the eyes pick up the information that would allow him to go on, to pick up information in the source text that would allow them to go on smoothly in the target text. Okay, so we can now, how can we formalize this in terms of Markov or partial observer Markov decision process? So we assume that we can assume that the translator infers from the source text these alignment groups. The alignment groups are mental constructs, right? So this breakdown rotura is a kind of a hidden process that goes on, and we can observe, or the translator produces these kinds of behavioral data. And here is a kind of a first idea how to conceptualize this. So we have here some kind of reading process, right? And then we have some kind of translation production process, and the translator goes through an assumed hidden states by which is the sequence of the alignment groups in the order of the target language. So alignment group 1 here would correspond, for instance, to breakdown, then alignment group 2 to off, and so on, right? And so the translator would try to generate those alignment groups. So these source text target correspondences, search in the source text for the clues to go on with the translation, and type out the translation. Now, from a point of view of the translator reads. So the translator takes in some source text information here and types out some translations here. Okay, so it's just so we can split up the activity units into actions and observations, and we assume here that is the point of view from the translator, what happens in the translator's mind. In the translator's mind, we assume that something like this are unobservable hidden states through which the translator goes. And the sequence of states is then connected here through kinds of transition matrices. So it goes from one state to the next state to the next state, and at each state emits somehow a kind of observation. So it means in this case source text reading. The translator reads the source text and here reads the target text. And then these transitions from one state to the next are also conditioned by some kinds of actions and by insertions and deletions. Now, what the free energy principle assumes, in addition, that an agent can plan in the future what is the sequence of actions and states that are most reasonable, that reduce best the free energy, that produce least clashes between my actions and my predictions. And this is conceptualized here in this pie. So, and in this expected free energy, so an agent would compute or assume maybe produce different paths mentally, and then decide which path, which sequence of states produces least free energy. So which sequence of states is most in line with the assumption that the translator will finish their translation and will not have many hesitations or doubts and so on. So this is an expected free energy, and that is computed at each point, and it takes into account preferences here. For instance, here the preference should be or could be that a translator would like to produce a high quality translation, or maybe the preference could also be that the translator should produce a gist translation, a rough translation, quick and dirty. And according to these different preferences, different kinds of paths, different kinds of transitions would be computed, or what the translator would consider this unconsciously, but different kinds of paths, and then react accordingly. Okay, so that's so far with respect to my part of the presentation. So that's the idea. So we have this partially observable Markov decision processes, and we want to try to simulate or to model the translation process within such kind of a model. The next step would be that Yusheng was friendly to lead us to explain to us a library of these partially observable hidden Markov hidden processes, which we can use then to model these processes. But before we go to that part, is there any questions with respect to this part? No? No questions? Okay, then I give over to Yusheng and ask him to give an introduction to that library. Thank you.
Yes, can you hear me?
Yep.
Yeah, great. So yeah, thank you, Michael. So the free energy principle has a corollary called active inference. which basically has a probabilistic representation of how the unobservable causes out there in the world generate observable consequences or our sensations. So many of the things there are about probability distributions, and some also has KL divergence, which we mentioned some time ago. So let me just first share my screen. Oops. Do you see my screen now?
Yes, I do.
Yeah. So this, what I'm going to do is just to go through this tutorial of active inference using a library called PYMDP here. And there is a paper that describes the details. So if you're interested, you can look into the details there from the paper. The PY means it's written in Python, and MDP means it's a Markov decision process. This library is available on GitHub, and they also have a documentation which includes this tutorial. So this tutorial would have several parts. It starts with some basics about probability distributions and how we can do some mathematical operations on these matrices and vectors. And then it will move on to an example of grid world environment where an agent is in this grid world and tries to move from one location to another. And in each step, it'll try to infer where it is and where it would be after taking an action. And the process of inferring these states, which is basically hidden from the agent, is through a lot of mathematical operations based on the active inference theory. So from there, we would have a lot of conditional probabilities and distributions, and we'll also get the entropy and the KL divergence for those. And what's needed to get the script running would be 4 parameters denoted as A, B, C, and D. And this would be the generative model of the external world. This is the world, something external, and this is the agent's probabilistic representation of this external world. And through these parameters, it'll infer what the external world is, what state it is in, and specifically in this case, its location in this grid world. And then after some basic ideas, we would move on to a loop, which simulates an active inference process, where in each step of the loop here, it calculates the expected free energy for each possible action, and then make a selection out of these possible actions based on the calculated expected free energy. It will choose the action that corresponds to the lowest level of expected free energy. And then we'll add another layer for planning. So that's the basic structure of this tutorial. Now, I've taken some notes here just to help us clarify some of the things needed. So we need 4 parameters. A is a matrix. It denotes the probability of observations under the condition of certain states. And in this example, the states are the locations of the agent. The observations would be where it observes it is. The states would be where it believes it is. This is the agent's belief or its belief over the external states. And the active inference process would be an update of this belief after some observations, and that has to do with the KL divergence, right? And matrix B denotes a temporal dimension, meaning the agent's belief of the current state based on its previous state and its action. So in other words, if I know that I have taken some action at the moment at my previous moment, and I believe that I was somewhere in my previous moment, then I would have an idea or a belief of where I should be, right? Where I expect myself to be if I have taken that action, and if I was in a particular location a time step ago, right? So that's matrix B, and C is the probability over the prior belief over observations, and in this example, it's the preference or where the agent wants to be, and D is a vector denoting the belief over hidden states, or in this case, it's the starting point. A, B are matrices, and C and D are vectors. Now, I'll come back to that later and explain the details as we go through the scripts. So for the script, we start with some basic operations. These are the functions that will be useful for visualization later on. This one plots the likelihood of a matrix. This one plots the grid world, the environment, right? The grid, like this one. It just plots this graph. And that one plots the location of the agent in this grid world. And this plots a probability distribution of the agent's belief as to where it is. So these are the functions to plot all these kinds of information. Now, the basics. So if we have a probability distribution, meaning the variable x being x taking all these values from 0 to k, then we would have a probability of x being each of these individual values, and altogether these would be a probability distribution represented by px, right? It's basically a set of numbers, a k+1 numbers right here, and altogether this would be a vector. So if we import utils, we can use that to generate some random probabilities, just as an example of how we can do the mathematical operations. Let's just randomly generate 3 numbers. This function will give us 3 random numbers. And since we're talking about probabilities, these 3 numbers should add up to 1, right? So we use another function here to normalize it so that they add up to 1. And if we print them in the format of a column, now this prints the numbers in the format of a column. We see that there are 3 probabilities, and altogether they add up to 1, right? So it's just a random generation of 3 probabilities. And then we would have a sample function here from utils that can sample the outcome. And you could see that these are randomly generated numbers. So the next time I run it, it will be different. For the sampled outcome, the next time I run it, it'll also be different. Now here it's sampled outcome number 2, and if I run it again, you see that it generates another outcome. But the what outcome it's generated, the sampled outcome will be related to the probability here. So it just simulates the probability distribution. Now there will be a higher chance of generating this result, or this result is just the index 0, and simply because the probability is higher, there will be more frequently sampled there. So these are what the functions do, and the plot beliefs simply just plot the probability distribution. For these 3 probabilities, we see this one is the highest, and this one is the lowest. So we see the probability distribution with 1 being very low. So those are the probability distribution. Those are the probabilities for one single variable, right? And in the same way, we can also do some operations on a conditional probability, right? The px given y, this is the probability of x under the condition of y. And we can, in the same way, we can generate 3 random numbers, 3 rows and 4 columns. It'll come down to a matrix here. And then we can print this in this way to show these numbers. And just because these are three random numbers, they may not represent probabilities. And if we normalize them, they will add up to 1 in each column. Each column represents a condition. And here the condition is y, as you can see from the mathematical equation. So the first column represents the condition that y equals 0. This column represents the condition that y equals 1, and so forth. And if these are conditions, then we would expect that each column would add up to 1. And that's basically what it does in the normalization here. So that's a random generation of the conditional probabilities. If we want to show the first column, then, or that's the probability of x given y equals 0, then we can just print this matrix and indicate column 0, which basically means the first column there, or the column that where the condition is y equals 0. And we print it in the form of a column, then we would see these three numbers, which basically refers to this column, right? These three numbers, and they add up to 1. So these are about the generation, how we randomly generate these numbers. Now we come to the calculations or mathematical operations of these conditional probabilities. If we have the probability of y, say in 2 cases, the first case has a probability of 0.75, and the second is 0.25, meaning that the outcome of y being 0 has a probability of this number, and the outcome of y being 1 has a probability of that number. And then we can have, if we assign the conditional probabilities x given y with this matrix that they're shown here, right? This is the matrix showing conditional probabilities, and these are the probabilities of the conditions. Then from there, we can calculate the probability of x, right, or the expectation of the value for x. Now, let me remind ourselves, these are the conditional probabilities. These are the px given y. There, px given y. And the vector there refers to py. And from py and px given y, we can get a dot product of the vector and the matrix. In linear algebra, the dot production is simply the expectation of each row of x, right? And that basically means the probability of x. It's calculated by taking this number times this number and plus this number times this number. And it does the same for every row. So eventually, this function will give us 3 numbers, or a vector containing 3 numbers. And these would be the probability of x for each value of x. And they add up to 1. So the only thing we need to keep in mind is this function, which gives us the probability of x. Now that's the basics. If we move on to the real examples, we would try to define these 4 parameters. So the example here is that the agent is in this grid world, and it tries to infer where it is. And it tries to infer where it would be after taking some actions, and what action it should take to arrive at its preferred location. Now, if we look at the agent from from our perspective, we would know where it is. But if we are the agent itself in this world, we would need to observe and we would need to infer where we are, right? So that's what the script does. Every step is an inference of the states, and the states means where it is, right? It's partially observable because it simply just cannot be very sure where it is. But it can observe something to infer where it is. So that's the observation and the states. Now, the A matrix is the probability of observations given states. It's just a given conditional probability that I've just described. If we define the number of states as 9 and the number of observations as 9, we say 9 because there are 9 locations here, right? From 0 to 8, there are 9 locations. And these are the number of states and the number of observations. Then we would initialize these variables. If we say that the A matrix is 100% certain, right? It doesn't contain any noise or ambiguity, then the matrix would look like this. The rows mean the states. Now, these are the conditional probability. So the columns mean the conditions, and the rows are the observations. Now, as an example, let me just describe what it means. The one in this corner here simply means the probability of observing 0, given that the state is 0, that probability is 1. And under this condition, every other probability would be 0. In other words, the agent seeing itself in location 0, or observing that it is in location 0, given that it believes it's in location 0 before the observation, that probability would be 1. So it always believes very accurately. Its belief is consistent to what it observes. After observation, it just confirms its belief 100%. And that matrix is just generated by the lines here. This just gives a created matrix, and this gives the number for this matrix, where all these are 1 and all the dark areas would be 0. So this function would plot the likelihood. Now, let's remind ourselves, there are 9 possibilities for its location, and the agent believes it is in one location, and then it observes the environment to confirm its location. What if its observation is not consistent with what it believes, right? Or in other words, its belief is not really 100% certain. The way we do it is by adding noise to matrix A. So this part indicates that the row number 0 and column number 0 in A matrix would be 1 out of 3, right? 1/3. And it basically means that the probability of the agent seeing itself in location here, location 0, under the condition that the state or its belief prior to this observation is also 0, that probability is no longer 1. Right? Its observation is no longer 100% consistent with what it believes, where it believes it is before this observation, and that probability has become 1/3. And if we assign 1/3 for this number and for that number, it means that there would be 1/3 probability of the agent seeing itself in location 1 when it believed it was in location 0 before this observation, right? Meaning that the observation is not consistent with its belief, or the probability of O is different from the probability of S, because A matrix is just a PO given S, right? So in this way, we add some uncertainty here and plot this. It will show some gray areas with equal probabilities. And in the same way, we can say that in location 6, now in the grid world, location 6 is here. We may define location 6 as an some kind of an ambiguous location where the agent might believe it is in location 6, but after some observation, it might find itself in say location 3, because that's very close. It might its belief might be inconsistent with its observation, and that's what it does here. If we assign these probabilities there, we would have some ambiguity and uncertainty in location 6. That's done by assigning these numbers, right? This indicates which part of the matrix, and this means the number for that probability. So 3, 6 means the row number 3 and column number 6. It is this location, and that probability is 1/3. So that's the way we define A matrix. A matrix is here, and the next thing to do is to define matrix B. Matrix B indicates where it would be, where it is now, given where it was a moment ago, and what action it has taken a moment ago. So the way it's defined is here. And in this grid world example, the actions were simply moving to different directions, or staying where it is. So we have these different directions for the actions, or stay where it is, or not moving, right? And if we define the B matrix as in this way, meaning if the agent moves up, then the Y would be -1, indicating that the rows would be one row above, right? And the X doesn't change. And if we define it with 100% certainty for B matrix, then all the probabilities of the next state would be 1. So it's very certain that if the agent takes a certain action, a particular action, and if it was in a particular state, then the next state would be almost certain, right? So B matrix it's a 3-dimensional matrix. It has the next state, the current state, and the action, right? That's the B matrix. So if we plot it, that comes the interesting part, right? If we say that the starting location is 1, 0, say 1, 0 is simply location 3, right? The first row and the column 0, the column 0. Yes, this function plots our location there. So if we assign starting location as this location 3, then it plots that the agent is here at the starting point. If in the simple case, let's just avoid those ambiguities in this observation and say that the agent is always very certain about its location at the starting point. In other words, if it is there, it will believe it is there, and it will observe it is there. If there's no inconsistency in this observation, then this belief would be concentrated on one single location, right? With location 3, which is here, with one probability of 1, and every other location would not be probable at all. The next thing to do is to define the actions, right? If we have all these actions, and if we say that the action it's taken after the starting point is to move right, then we can use the same function to plot its next location using matrix B, because matrix B defines where it would be after this location, after this action, right? And if we have the start, the starting location and the action, then from matrix B we would have next state. And if we plot it, it shows that the next state is here. What it basically means is that from here to here, after taking an action of moving to the right, it becomes here, right? And in the same way, from this location, if we say that the agent takes another action of moving down, and from the B matrix, we would see that it moves down there, right? These just plots what happens. For C vector, it's the preference, in other words, where the agent wants to be, right? The desired location. If the desired location is assigned to be 2, 2, let me remind ourselves, 2 and 2 is just location 8. If we say that the preferred or desired location is location 8, and that has a probability of 1, it means that the agent is very sure that it wants to be in location 8, and it doesn't want to be in anywhere else. And if we plot the belief, we see that the preference for location 8 has a probability of 1, and all the others were not probable at all. For vector D, that's the starting point. If we say that the agent starts from location 0, then if we plot the belief, its belief is also concentrated to 0. Now, that's basically the way we define these variables. So we have 2 matrices and 2 vectors there. The next thing to do is to write all the functions for the hidden state inference. In other words, the agent is trying to infer where it is from the A and B matrices. A and B matrices would be its probabilistic representation of the external world, and the result of this inference is where it believes it is in this external world, or the state, the hidden and unobservable states in this world based on its internal representation of the world. And we call that the posterior belief after some observation and some action, or the probability of observation of states given observation and action. And that's from A and B. The mathematics works this way. It's just the sum of 2 logarithms for a particular observation and a particular action. The same mathematical equation can be written as a function here, where the infer states just infers the hidden states from the matrix A and the matrix B, and it gives us the inferred states. It comes in the form of a probability distribution. And in each step, if we say that a moment ago it was in location 4 and it has moved up, then from this equation, which basically is matrix B, it's encoded in matrix B. So its previous location was number 4 and it moves up. Let's just say after moving up, it observes it is in location 1. Now these parts would assign these to the variables. Location 4 is here, location 1 is there. Say it believes that a moment ago it is in location 4, and it knows that it has taken an action of moving up, and now it should believe it is in location 1, right? And if we say that with this prior belief, the agent tries to observe the world and infer its location, and the result of that observation also tells it that it is in location 1, then its belief is confirmed, right? So this is what it believes based on the action and the B matrix, its prior belief. This is the observation or the belief after observing the external world. And if we say that the observation is in location 1, which means it's consistent with its prior belief, then if we plot its belief after this observation, it's 100% sure that it is in location 1, right? Simply because its prior belief is confirmed by its observation. But what if it observes in another location, right? And if we if we assign number 2 to this observation using the same process, in other words, if the agent believes that it was in location 4 a moment ago, and it has taken an action of moving up, based on its internal model, it will believe that it should be in location 1. But now, if we assign number 2 here, it means that after this action, the agent now observes it is in location 2 instead. And now that will confuse it a little bit, right? That will add some ambiguity and uncertainty there. And if we plot the belief, we would see that it has half probability, 0.5 probability of being in location 1, and it has half of the probability being in location 2, right? It just gives us a distribution of the probabilities. And if we go a step further and add some more ambiguities for matrix A in a way that I've just described, then we would have a very noisy distribution of probabilities, meaning that the agent is no longer that certain about where it is, right? There is still a chance that it might end up in, say, location 8, although it has a strong belief or the highest belief in location 1. And if we continue with more noise, then we would have another distribution here, right? From the discrepancy between the observation and the belief. It believes it would be in location 1, but after this inference, after this action, it observes it is in location 2, and then that will confuse it a little bit more, and that will add up more uncertainty, so that the probability here is lower, and the probability of 2 becomes higher, and the distribution becomes more evenly distributed. Now, in entropy terms, we would say that the entropy here is lower than the entropy here, and the entropy in this distribution is simply 0. All right. So that's what it means by entropy and probability distribution, and the definition of these matrices and vectors, and how the mathematical operations work. The next thing to do is to choose an action to arrive at a desired location. Now we have matrix A denoting its the relationship between observations and beliefs, and matrix B denoting a temporal dimension of its belief, and C as the preference, meaning where the agent wants to be, and the D is the starting point in this grid world. The next thing to do is to write a few functions to infer its state, and then choose one action that will take it closer to its preference. It wants to be in a location, and it will calculate the corresponding free energy for each action and choose the best action to arrive at this desired location. Now, these functions simply get the expected states from matrix B first. It means the agent knows that it has taken a certain action and that it believes it was in a certain a particular location a moment ago, and it has a matrix B, which is the mental model, it will have an expected state, right? What if I have taken this action, and if I was in this location a moment ago, where would I expect myself if I take this action, right? And in the same way, it has an expectation of observations. If I take that action, what do I expect to observe, right? This is from matrix A, and if matrix A is noisy, then the observation may not be consistent with its belief. We also have entropy of matrix A. This will give us the entropy for every column of matrix A, meaning the entropy of all observations for each individual state, or the observed location of the agent, the entropy of its observed locations for each of its believed locations, right? So we see the logarithm, the weighted sum, and the weight and the sum. So that's just the definition of entropy. And we also have the KL divergence between the expected observations and its preferred observations. In other words, how different are my expected observations from what I want to observe. I have taken an action, and that action gives me an idea of what to expect or where I expect to be in. And that will give me an idea of what I should expect to observe. And then I will see whether that expected observation is getting closer to what I want to observe. So that gives us an idea of KL divergence there. These are all put into the calculation for free energy. So if we just run the example and give a starting point, which is in the middle, and if we say that the agent is certain of its belief, right? At the starting point, its observation and its belief is consistent, and then this is the grid world. It starts from location 4, and if we say that the agent wants to be in location 1, 2, which is location 5. Right, 1 and 2 is location 5. So it starts from location 4 and it wants to be in location 5. Now, the location 5 is assigned to C, and location 4 is assigned to D. So this plots the belief of where it is at for the preference. And if we say that there are two possible actions for the agent from location 4 to location 5, it either moves left or moves right. What it does there is just to do all the mathematical operations that I've just described, and then get the expected variational free energy. The free energy is calculated from what we got in terms of the expected states, the expected observations, the entropy, and so forth. From the entropy, we get a predicted uncertainty for this action. Right? This is a dot product, and it gives us an expectation or an average entropy level for this action. Meaning, if I take an action of moving left, what level of uncertainty should I expect in my observations? And in the same way, it has a predicted divergence, KL divergence for this action. Meaning, if I take an action of moving left, how different would my expected observations be from what I expect to observe myself in? Now, C denotes that it wants to be in location 5. The divergence tells it whether, now if I move left, are my expected observations being more different from location 5, or is it getting closer to location 5? And the sum of these two, uncertainty and the KL divergence, the risk and the ambiguity, would be the free energy. Same thing for another action. If I move right, what would be my predicted uncertainty or the average entropy? And what would be my predicted divergence? And altogether, that would be my expected variational free energy. If we run this part, it'll give us two numbers. After all these mathematical operations, it tells us that the expected free energy of moving left would be 36 something, and the expected free energy for the other action is 0. Very, very small there. The active inference theory would say that the agent always tries to choose the action corresponding to the lowest level of free energy. And if we convert these two numbers to probabilities for these two actions, we see that the probability of the agent moving left is very, very small, right? Nearly negligible. And the probability of its moving right is very high. This corresponds to the level of expected free energy, right? The low level of free energy there. If we look at this, the grid, it means that from location 4 to location 5, it will be almost 100% certain that the agent will choose to move right in order to arrive at its desired location. So that's the basic idea. We have basically done all the operations for active inference, and if we put all these into one single function, it'll look like that. It'll become more convenient later on if we want to write a loop out of it. Now, this function calculates the expected variational free energy based on the agent's internal model, these matrices and vectors that we have just defined, and its chosen action. For each action, it'll get an expected free energy. For each current state, it'll get an expected free energy for the next state. So the result of this function, this function simply returns a number for G. So we've done basically everything. And to get it running, the way we do it is to define a class of the in grid world environment. This is the external. We don't really need the matrices and vectors here because this is simply the external. And the matrices, these parameters are the agent's probabilistic representation of this world. So if we define this world and then define the model, the internal model for the agent, meaning these A, B, and C, and D parameters. And if we define the actions, then we can just run it. So if we initialize it with a starting state of 1, 2, 1, 2, which is basically location 5, if we designate that as the starting point, we can just write a loop with all the things that I have just explained with A, B, C, D, and actions and the environment. If we denote that the time step, now the T refers to time step, to be 5, it'll run 5 times and then infer each of these steps. It will infer the hidden states and then choose an action in order to be closer to this preferred location. So if we put those components into the loop and run this loop, we would see that the agent starts at this location, which is basically location 5, and its belief is very certain. It believes that at the starting point, it was in location 5, and it observes itself in the same location. So that belief is confirmed. And the next step is that the agent has chosen an action based on all these mathematical operations, the best action it should take to arrive in the desired location. And now, after that action, it observes the world and sees itself in location 2, which is location 8. And that's the desired location, right? It has taken an action and then arrives at the desired location. And the next step, since it is in the desired location, it'll choose to stay there because that will correspond to the lowest level of expected variational free energy. And for all the next steps, it'll just stay there because it's already in the desired position. In this example, it's very simple because the starting point is just one step away from the desired location. But what if it starts somewhere else with that would be slightly more complicated. Say it starts in this corner, location 0 here, and it wants to be in location 8. There would not be a way for it to choose the first action because whatever it chooses at the starting point, the expected KL divergence would be the same if we compare that location, the posterior belief of that location and the probability distribution for the preference. Every single location near location 0 would be would correspond to the same KL divergence to location 8. So it will have a problem in choosing that action there. This part of the script shows this fact, and the way we can improve its operation is by adding another layer, which is a policy or a planning, or what series of actions is appropriate. Say if it moves right, right, down, down, it'll arrive at this location, right? Or alternatively, if it moves down, down, right, right, it'll also end up in the desired location. But which of these series of actions would be most appropriate? Which of these series or policies or planned actions would correspond to the lowest level of free energy? Now that will come into the mathematical operations in this part. We basically use a very similar way of writing the functions, but adding another layer of policy and another loop. And the expected free energy would be the total expected free energy for all the actions in the policy. So in the same way, we define these functions and then write another loop with planning, right? It's a similar loop, but with planning. So it takes on an additional parameter here, which is the length of its policy. And here, if we say that it only considers 2 actions for the policy, and if we have the same number of time steps, then if we run the same thing as saying that the agent starts in location 0 and it wants to be in location 8, and when we run that that loop, we'll see that now it believes at the starting point it's in location 0, and now it stays there, and then it, in each step it'll try to infer an action to take, and then eventually it'll take the corresponding action to be closer to 8, and then when it arrives at 8, it'll just choose to stay there because that is the preferred state. So that's basically how the script works. And in summary, we just need these parameters, and the way it works is just by writing several functions: its expected states, its expected observations, the entropy, and the KL divergence. And free energy is simply the average entropy here, which they call the predicted uncertainty, and the KL divergence. For each action, there will be a free energy here, and it'll always choose the action that corresponds to the lowest free energy. So that's my part for the script. Yeah, hopefully it will give you an idea of how to play with it and how to adapt it to the translation process.
Okay, thank you very much, Yusheng. Are there any questions? Otherwise, I will go on and talk about how to adapt this idea to translation, to the translation process. No questions? Okay, so we were giving a thought of how this idea can be adapted to these kinds of translation. So I showed this graph previously, and Yusheng went through these different parameters, right? We have an A matrix, which is a conditional probability of the state and the observation. Then we have the B matrix, which is the probability of going from state 1 to state 2 to the successive states, given there is a kind of an action that takes place. And then we have this pi, this policy selection. We have a computation of free energy, and we have preferences, and we have preferences for the observations C and preferences for the hidden states D. Okay, so we have this data here from the translation process and want to adopt the framework that Yusheng just explained to this kind of a situation. How can we do this? So there is I devised, or we devised this this notebook here, and the idea is that we read a segment. So a segment and would be read, and then we see the source text and the target text, the translation of it. So we know a translation, and this process would predict how difficult it was to produce that translation for a translator. Okay, so we have the translation from a human agent. So the translation and the translator has produced the source and the target text with the translation, and has a certain kinds of behavioral data with a certain kind of effort metrics. And the question would be, how can we simulate or how can we model the effort put into producing this particular translation? So we read a segment from a study. A session initialized the matrices that Yusheng talked about, the ABCD matrices, then run this partial observable Markov decision process, which generates a sequence of activity units. So these activity units that I talked about previously, maybe a generalization of it. We would compute or evaluate the effort that this sequence of produced AUs represents, and compare this with the effort that was put into by the human translator in the beginning. Okay, so and the idea would then be to initialize, to play around with this ABCD matrices in such a way that the effort that is modeled here in this process approaches that of the human translator. We would then need to formulate, what does it mean, effort? So how do we compute? How do we specify? How do we compute an effort? So can it? So we were talking about action perception loops. And for a translation, for a segment translation, one would need to generate a couple of action perception loops. So one way of computing the effort produced by a translator would be the number of action perception loops. Another could be to count the number of insertions and deletions and the number of reading operations that takes place, or simply the number of activity units, the duration, how long it took to produce this. So there's various ways of how to compute an effort based on the original human translation and of that model, the partial observable process that simulates this translation. So this would be one thing, to formulate this effort metric. The second one, then modify these parameters A, B, C, D, so that we approximate the effort produced by the human translator, and then we compare different translations and see how these parameter settings then can simulate the different ways of exerting effort. So there is the script here that I've prepared. So we read first the data from the TPRDB. So we read the source text, the target text, the activity units, it should be here, the alignment units, alignment groups, and some kinds of mapping of this. So here are a couple of functions. This read TPRDB, so this reads the data source and target text from the data. Then it produces an STTT mapping, and this function here would produce the next assumed internal state. So how does this look like? Let me just go. So this exercise could be based on a number of sessions that we have. So we have here this number of sessions. How many is this? 10 maybe, something, from the BML-RE study. And I will just look into 2 of those sessions and with segment 1 here. So if we look into this BML-12 or BML-12-RE a study that doesn't matter so much. It's the same, it's only differently aligned. If we look into the segment 1, this is a text about sociology, and the source text is sociology is a relatively new academic discipline. That's the source text. And this text has been translated by all these different translators. And if we look into segment 1, the translation, the target of these two translators, P08 and P28, produced exactly the same translation into Spanish. La sociología es una disciplina académica relativamente nueva. So this is the translation of this sentence, and these two participants produced the same translation. But now, if we look into, and we can get this data by running these functions here. I hope I have. So if we run these functions, we grab session of translator 8 and the first segment. Then we run this read TPRDB, we get the source text and the target text and the sequence of activity units that have produced, by which this translator has produced the target text. And with this function, we get the mapping, the mapping from ST to TT. So the alignment relations between from the source to the target and from the target to the source. Here, what we add this kind of dummy symbol in the beginning of the source and the target sentence, so that both the source and the target sentence start with this symbol, with position 0, right? And there's a similar symbol, dummy symbol at the end, to make sure that we can say the translation ends at the same position here. And these one just fill up the make sure that the source and the target language have the same length by adding these kinds of dummy symbols here. Okay, so if we look into now what comes out here, we have the source text. This is the first one is this dummy symbol, right? So we can say the source and the target are aligned here. Okay, so the symbol 0 is aligned, and the last symbol here 2 is aligned. Okay, and in the middle we have sociology is a relatively new academic discipline, full stop. Okay, and here we have a mapping of, this is position 0. Okay, position 0 maps. So this is the STTT mapping. It says that position 0 of the word number 0 maps into word number 0 in the target side, and word number 1 in the source maps into word number 1 and 2 in the target language. Means sociology is translated here as la sociología. Okay, otherwise all these alignments are 1 to 1. You can see there is so there is 2 to 3. Word 2, which is this one here, maps into word number 3, word number 4 into 5, and so on. So all these no, there's kind of swapping also. Okay, so we have here a target alignment, and here we have the reverse, a target to source alignment. So this looks from the source to the target. This dictionary looks from the target to the source. Here, for instance, we see that word number 1, which is la, okay, translates as sociología. Word number 2, this one here, also translates into sociología. So we have this 1 to 2 alignment here. This graph now tells us what is the next source text word, so that the translation is produced in the order of the target language. We have seen previously, I've talked about that the translator produces a translation, usually, often, in the order of the target language, where the eyes go around in the source text and search for the clues to produce the next target word. So we assume that we will have at an output a smooth production of the target sentence in the order of the target language, but the translator would look around in the source text to find the next word. Okay, and this dictionary here would tell us what is the next target word, so that the next which is the next source word so that I can produce smoothly the next target word. Okay, here we see the activity units by which this particular translator has produced this translation. So it has, according to this counting, 34, 35 activity units. And we can see that here is lots of reading. So it's only a part. There's, of course, much more information in these AU tables. Here, it's only taken out a little bit. Here we can see what was edited and which words were edited. So this should correspond to this source and target mapping. Then here in square brackets, we see a deletion, here an insertion. And so we see that this production of the translation is quite fragmented, right? Okay, now if we take another, if we take this other translator, this 128, and read the source segment with this from this translator, then go through the same process, then we see here that, well, the source and the target is the same. The alignment, I don't know, maybe it's also similar, but if we look at the number of activity units that the translator needed to produce this translation, it's quite different. It's only 11 activity units, okay? And so the idea would be in this task, we know what the translation is, and we want to model these kinds of processes and assess how difficult it was for a translator to produce this particular translation. Okay, so we are a little bit time over, but so everyone who wants to leave now can leave, but I'm just going on because it's part of that homework that I would ask people. So for those who want to have a certificate of this class, should look into this thing and do some homework related to this task. So I would ask them to stay on for a little more time, 10 minutes or so, or 15 minutes or whatever question that might pop up. Okay, so this is the data that we get. And we can, with this, initialize the all these ABCD matrices. Okay, so the A matrix is the probability of the observation given the state. And the B matrix is that Yusheng just wonderfully explained. Thank you so much for your very nice explanation and in detail. So we have these two matrices. So this is the matrix of the states. What is the transition between the states given a previous state and an action? Here we have all these functions that come originally from the same from that script that Yusheng explained, and here slightly differently initialized the A matrix, because the A matrix in our example is a mapping of the internal state, so of the source text or the alignment groups into the observations, which is the translation. And the B matrix, as I just tried to lay out, is the kind of transition between successive alignment groups so that the translation would be produced in a linear order. So if we look at this A matrix here, the A matrix is an STTT alignment. So this, if you have looked into statistical machine translation, that is what often pops up there. So we have a source target alignment where the rows is the source text and the columns is the target text. So remember, this upper and this lower point were artificial starting points, right? And here we say the rows is the source words and the columns is the target word. And we have a translation of 1 to 2 translation. So we have the word 1, for instance, translates into word number 1 and 2 here in the target language. Okay, so this is a kind of an alignment graph between the source and the target. And it indicates the conditional probability, given we are in a state S, which is a position in an alignment group, what is the observation? And the observation is the target text in this case, the segment. Here, the B matrix is the matrix that indicates what is the next word in the source group alignment or in the alignment group that produces the next target word. And here we have three actions: insertions, deletions. We have here, no? We just assume that we have three actions: insertions, deletions, and reading. Okay, so that is a very reduced number of activity units. One could also go ahead and increase this number, but starting with these three actions, we have a B matrix here that has at position 0 the insertion. So in what state is the translator likely to see himself when they insert a word? So assume they are in position 1 and insert, they are in position 0 and insert a word. So they will be most likely, they will have they think with certainty that they will be in position 1 here, right? When they are in position 1 and they choose to have an insertion, there is an equal probability to be in that position 1 or 2 here, which is just the ambiguity that we had here in this alignment between 1 and 2. Okay, so if a translator is in position 1, the next position could be here the translator is in position 1. The next position could be 1 or 2, which is here encoded in the B matrix, and shows because there are two likely probable situations here. It has this gray highlighting here. Okay, now we come to the same process that Yusheng explained, and all these functions that Yusheng had explained, and we have this generative process here again. So obviously we changed a little bit the actions. We have insertions, deletions, and reading. And when there is an insertion, the agent will add a translated word to their translation. So we know what is the translation that the agent aims at, which is encoded in this string here. And this is the translation that the agent actually produces by going through the states. And here in deletions, then we just take out. So there was a kind of a word in the translation, and this is then replaced by this dummy symbol. For insertions, we add a word to the translation at a position in which the translator believes to be. And here, the translator deletes a word by inserting this dummy word. By reading, nothing happens. Yeah, reading, no output is produced, and nothing happens in the translation. Okay, so now we can run this simulation exactly as Yusheng just also showed. We have the number of states, which is the length of the source string, the number of observations, which we take here to be the number of target words. Then we have three kinds of actions: insertions, deletions. And then we can create the A matrix with the function that I just explained, where we have the source target alignment relations. Here, the B matrix is the sequence of alignment groups. So in an order that would smoothly produce the target target sentence, the translation. Here we initialize the C. So the C is the preferred, the preference, right? And here we just say, basically, the translator prefers to be at the end of the translation. So the translator prefers to finish the translation in such a way that for each for each successive word that they produced, the probability will increase. So they start with a low probability for word number 0 or 1 and so on, and towards the end these preferences become higher. Okay, this D vector is the starting point. So the translator starts at the beginning of the sentence at position 0, and the C vector would in this case express the preference to step through the target translation and produce the sentence. And then if we run this, so here it starts with a starting state here, and we have exactly the same procedure that Yusheng just showed with the ABCD matrices, which are initialized here. And then we have a different policy length that we can set, and we can say a number of steps in that process. And we can see here that the agent starts at time 0 and believes itself to be in position 0. That's the beginning. So then the most likely, the action with the lowest expected free energy is an insertion. This insertion only produces this dummy word here. Maybe it could be changed that the translator actually produces the first word. Then the agent considers, well, this is a reading action. So a reading action, nothing happens, right? This at a point 2, at timestamp 2, the translator still is in location 1 and considers now to make an insertion, produces here this insertion, and then again it's in the same position, and then there is a warning because we already produced the same word. Then steps forward, another insertion produces the verb which is at this position, and then we have here so basically these actions with the least expected free energy are all insertions, as you can see here, right? But here we can see that swapping. So here we have this is the location in the alignment group, and here we can see that the translator goes to location 7 instead of 4, because just there is a kind of reordering in the source and the target language. So in order to produce this next word here, disciplina, the translator needs to go into source position 7 to retrieve the word that would produce this translation here, and then goes back to translate to position number 6 to produce this word number 4. What happens here? Relativamente, and so on. So the translator produces here the translation by going through a number of insertions, readings, and deletions, and so on. One could then say, okay, at this position 10, the translator is at the end, so one could stop here, but it goes until the end. So one could add actually a conditional question: has the translation been produced? Then stop here, because there is no point in going on with these observations. Okay, all this stuff here, that what this function does is now recorded in a variable called history, which collects the history of these activities here, and one can print out this history, which is this history here. Okay, so the task that I would ask for students who would like to do some homework would be to write a function that assesses, that computes a kind of an effort. What kind of effort does this sequence of actions imply? And this function should be such that it can be applied to this AU, to this table here. Okay, this is the AU type table. It only shows these these columns here, and this function should compute an effort indicator for this AU table, and equally an effort indicator for this table, and then go ahead and initialize, manipulate these initializations of the ABCD matrices such that it approximates, oops, where is it? That it approximates the effort metric, so that we can simulate or model the effort that a human translator produces. Okay, so load the different data from this TP-RDB and then run simulations by differently initializing these matrices, determine that a setting of these matrices that best reproduce the effort metrics, then load another session. So we have this number of different kinds of sessions here. Okay, so we have, oops, where is it? We have these, yeah, I just showed these two sessions. This is a very short one. This is a quite different effort indicator it would produce, but all these are translations of the same text, and once we can maybe figure out what are actually indicators of effort, how can we manipulate these ABCD matrices so that these effort indicators become a little bit close to another, one can see whether those indicators then also apply for the other kinds of sessions that we have, so as a test set, so to say. Okay, so that would be the idea. Any questions with respect to that? Okay, I will make this script available over the Dropbox. It does not run on the CRIT server because it requires Python 3.9 and the server has only 3.6. But I assume it would run on well, it runs definitely on Google Colab, or if you download, as I did, Anaconda, it has, I think, Python 3.10 currently. So we can maybe arrange how we can do this. There is lots of material about active inference on the web. Here we have this fantastic book that's free, and it gives a very good introduction to active inference. There's a group, active inference group here, and they have a reading group actually that starts on 20th of June. They discuss this book here, which is, I guess, a very fundamental reference for active inference. And they discuss this in detail, go through each chapter in a couple of weeks to discuss this active inference. So I would suggest, if people are interested in this, to go to join this group here, cohort number 4. There are also documentation of this particular library online. This documentation that Yusheng just showed is here on this link, and then there are YouTube videos which are very interesting and instructive also on YouTube to look into this library here, where those people who actually created these libraries explain how that works. Otherwise, I would suggest we can meet. So the idea would be that this is a homework for students who want Hauptschein now, I guess, and also yes. So I could suggest that we can meet every 2 weeks, or whenever there's a question, we can meet and discuss what are the problems, how things should go on. We can set up a kind of a network. So I would very much encourage to work in groups for this, because there are a couple of different tasks. So for instance, formulate the effort metric. There's different ways how to do this. Somebody could do this. That could be done independently from playing around with these different matrices and initializing them in different ways. So I think this whole thing can be very well distributed over several groups or in groups over several people, and then they can kind of coordinate how they want to integrate these different efforts. Yes, and I'm very happy to meet and to discuss over the next couple of weeks how we can proceed with this. Okay. Is there any feedback? Any question? No? Everybody would have an idea how to address this. So I zip this and I put this into the Dropbox folder and send a mail. And by the way, also all these videos, all these recordings are now on YouTube and in the Crit channel on YouTube. You can watch them, and I will also add this particular recording then to that channel. Okay, so I stop recording. Yeah, so I was of the understanding that it should be returned by end of July. So that would be almost 2 months. And yeah, so I would hope that everybody can then so if you play around with this and you come you can generate a notebook and then just hand this in and document what you did maybe and what changes, how you played around with this, either inside this notebook or maybe write this in a form of a paper or somewhere. What you did and what kind of problems you faced and what solutions you had and what ideas and so on. But as I said, we can also, I'm very happy to discuss this on the way eventually. Is that okay? Yeah? Good. Some questions from remote? No? Maybe in the chat box? Yes. Okay, so what is this question? For students from NIT, we need to make group within our domain. What is the domain? I don't know. What is, can Jingesh, what is, I don't know. I guess Raju will coordinate this somehow. And if you have any doubts, please come back, and I'm happy to sort stuff out. A domain is participants from India as compared to participants from Germany or from USA. No, well, I mean, you can mix up groups as you like, really, whatever you prefer. So if someone from India wants to work with someone from Germany here, that would be welcome too. Okay, but then if you hand in this work from groups, it would be good to make clear who did what in a notebook. Okay, so that I can figure out a little bit the contribution of everyone. Okay. Yeah. So if there's no question, then please, if they right now, then please send a mail and maybe we can clarify in that way. Otherwise, I would like to thank everybody to come to this exhausting introduction to empirical TPR, and I hope you learned some things and had fun. Of course, I also hope you will go on with this research. See you next time then. Thank you so much. Bye-bye.